Okay, so more rounding. We're instructed to round each of these numbers to two significant figures. So we're going to keep the ones place and the tenths place. So in this first one, we're keeping the 3. The decider is the next digit, 7. 7 is 5 or greater, so we round this up and we write 5.4. Here we're also keeping the 3, but now the decider is less than 5. It's a 4, so it rounds down and is 5.4. 5.35, rounded to two significant figures. The 5 tells us to round up to 4, so it's 5.4. This last one, rounding to two significant figures, again, we're keeping the 3 in the tenths place. We're only going to look at the first digit that we're dropping, the 4. We don't care about the 9. I don't care that the 9 may round the 4 up to a 5, which would tell us to round the 3 up to a 4. The 9 doesn't mean anything. So just look at the first digit. So this would remain 5.3. Okay? Any questions about that? In multi-step calculations, you do a calculation, you get an answer, and then you have to do some other stuff, and you take these two answers and you put them together. We run into that a lot in Chem 1A. We do not want to round our intermediate results, because when we do that, we can introduce what are called rounding errors. And they can be significant at times. So what we want to do is only round the final answer. But we have to keep track of the significant figures as we go along. So here's an example of a mixed operation problem where we've got multiplication mixed with subtraction. Okay? And there's a bunch of problems like this on that worksheet. So what we need to do is we need to look at the result of the subtraction, PEMDAS, P-E-M-D-A-S, please excuse my dear Aunt Sally, right? Parentheses, exponents, multiplication, division, etc. So we're going to do what's in the parentheses first. So when we take 5.489 and we subtract 5.01, your calculator will give you 0.479. We need to consider the rules for the subtraction and identify but not round off the number. We need to identify the last significant figure. So the rule in subtracting is you count decimal places. This one has 3 decimal places. This has 2 decimal places. So this result, if it were my final answer, should only have 2 decimal places. So I underlined the second decimal place. That is the uncertain digit. I'm going to let the 9 come along for the ride, because I don't want to round it off and maybe cause some errors. But now when I look at this number, because the 7 is underlined, I recognize that this has 2 significant figures. Coming from the subtraction, I was concerned about number of decimal places, but now when I'm going to take this number and do some multiplying, I have to be concerned about how many sig figs. So then when I multiply all of these together, this one has 3 sig figs, this is 4, and this one, because of where it came from, should only have 2. So here's what my calculator tells me, and I'm going to round that off to 19. Any questions? So what I recommend doing with intermediate values is to always write, on these they're pretty straightforward. Sometimes your calculator will give you, like 9 digits. Do I have to write all of those down? No. Minimum is write down 2 extras past the uncertain digit. Okay, so let's do these. I think it's a good idea to just do the calculation on your calculator and write down the result, and then go back and look at sig figs. So here we've got 3.10007 times 9.441 times 0.0301 divided by 2.313. And I get a mess. 0.380873153. Did I do it right? So it's a good idea, always do the calculation with me, and call me out when I make mistakes, because I do. We have multiplying and dividing. Those use the same rule, counting number of sig figs. So we look at this one, that one's got 6 sig figs. This one has 4 significant figures. This one has how many? 3. Leading zeros don't count. So far this is the winner for the smallest. And this one has 4. So the smallest number of significant figures is 3. So I need to round this to 3 significant figures. That 0 at the beginning doesn't count. There's the 3, the 8, and the 0. So I like to underline that. And then we're going to look at the next digit, that's the decider, and that tells us we need to round this up. And so the answer is 0.381. Any questions? This result reflects the precision of those measurements. This one, only having 3 significant figures, reduces the precision of the overall result. Okay, let's look at this one. Just do it on your calculator first. You don't need to do it in separate steps. Plus 132. So I do the math, and the calculator says 120.961. Adding and subtracting. Both use the same rule. I'm looking for fewest number of decimal places. So this first number has 3 decimal places. The second number has 1 decimal place. The third number has 2 decimal places. This has the fewest number of decimal places, 1 decimal place. So I'm going to round this off so that it has 1 decimal place. My decider, the 6, tells me I need to round the 9 up to a 10. And so the 1 is going to carry over here. 121. But I need 1 decimal place. It's the 0.0. Any questions? It's always nice to put a box around your final answer. Okay, in the third example, we have multiplication, we have division, and we have addition. We have 2 different rules that are going to be used. So we can't just do this based on one or the other. We have to consider these sets of operations separately. So let's do this adding business that's in the parentheses. 44.11 plus 1.223 equals. So that is 45.333. I don't want to round that off, but I want to note where the last significant figure is so that I can deal with the rest of the calculation. So adding, we're looking at decimal places. The first number has 2 decimal places. The second number has 3 decimal places. So this should be rounded to 2 decimal places. That would be that one right there. I'm going to leave the other 3 there. I'm not going to round it off. But now when I look at this number, how many significant figures is it going to have if it's rounded? Sig figs, not decimal places. It'll have 4 significant figures. I can't tell that it's going to have 4 significant figures just by looking at this. I've been doing this for longer than some of you have been alive. And I wouldn't do that, just guess by looking at it. I'd do the math, I'd look at the result and write it down and take care of it. So now what we're going to do is we're going to take 2.5110 times 21.20 divided by this. And I'm going to write down the result. So now I'm looking at multiplying and dividing with this number and these two numbers. So now I'm looking at number of significant figures. This one has 1, 2, 3, 4, 5 sig figs, 4 sig figs, and this one's 4 significant figures. So this answer should be rounded to 4 significant figures. 1, 1, 7, 4. This is the 4th significant figure. I look at the next digit, it's less than 5, so I round it down 1.174. Any questions? When you have adding or subtracting mixed with multiplication or division, you have to do those operations separately so that you can compare the sig fig, because the rules are different. Here we had two different operations. We had adding and subtracting. I don't need to do those separately. They use the same rule. I can look at number of decimal places and figure this out without doing separate things. But when I have adding with dividing and multiplying, then I have to do it separately. This next one, I've got multiplying and adding. Again, I need to look at the individual pieces to get the correct answer. So we do the parentheses first, 12.01 times 0.3. So that result is 3.603. How many significant figures does that result have? It should have 1. This one has 4, 12.01, but 0.3 is only one significant figure. So I'm going to underline the first digit. That's the uncertain digit. I'm going to keep the rest of it for the calculation, but I'm going to know that that has one significant figure and it's in the ones place. So then I'm going to take that, which is still sitting in my calculator, and I'm going to add 4.811. And I'm going to write down what the calculator says, 8.414. And now I consider the rules for adding, which we're looking at fewest decimal places. Well, this has 3 places after the decimal point. This number, this is the last significant digit. This one ends in the ones place. It has no significant figures that come after the decimal point. So I need to round my answer to the nearest 1. So it's the 8, and I'm going to round this to 8. Any questions? So we've been talking about precision. Precision and accuracy are two different things, and it's important to understand the difference. Let's think about throwing darts or shooting arrows. So you've got a target, right? We'll do arrows because they're easier to draw. So we're aiming for the bullseye, right? The center of the target. So if I hit the center of the target, that means I'm accurate. I'm getting close to what I was shooting at, right? What if I shoot several arrows and they all end up here? They're really close together. I'm very consistent, but I'm consistently wrong. I'm up and to the right. I need to adjust my aim a bit, don't I? These are considered precise. They're very close together, very reproducible, but they're not accurate. This one is very precise. I'm sorry, very accurate. Just one shot, you can't tell if it's precise or not. Let's put some blue arrows in here. Oops. What if my blue arrows, they kind of just dance all around the bullseye? None of them get into the bullseye. That's not very precise, right? But if I took those and averaged them, the average would come out really close to the bullseye. So that means taken together, they are accurate, but they're not precise. So accuracy and precision do not necessarily go together. What we'd like to have is accuracy and precision. So taking a hypothetical experiment with three students, A, B, and C. Give them a 10-gram lead block. So we know that it's 10.00 grams. And say, here, weigh this. They each weigh it 4 times, and they record their results, and then they record an average of the masses that they got. When we look at this table of numbers, we're like, just looks like a bunch of numbers. So what we often do is we will graph things, because this helps us to see the patterns that are happening. So here we made bar graphs. And so the height of the bar represents the mass for that trial. And then we can see that there's a lot of variation in this one, right? From 9.79 all the way up to 10.49. This person's masses are all over the place. That is not precise work, okay? And to measure accuracy, we're going to look at the average. So this blue line is the 10 grams. That's the true value. The average of this student's results is up here. It's significantly above the true value. So not only is it not precise, it's not accurate either. That student gets a D, right? Not good. Student B weighs that same object 4 times. These values are all very close together. That shows that this person has good precision. They're very consistent. Unfortunately, they're consistently wrong. When we look at the average, it's significantly below. And we'll talk about how that could happen in just a minute. So this is not accurate, but it's precise. And student C knocked it out of the park. Okay, good consistency, good precision, all the values are close together. And of course, we're talking in sort of quantitative terms. If we really are interested in this, then we have measures, actual quantitative measures of how close is close. But we don't care about that right now. So these are all close together, and when you find the average is 10.01. That's very close to the true value of 10.0. So this student was accurate and precise. Okay? So there are 2 types of error that cause our measurements to be inaccurate or imprecise. Random error is what it sounds like. It's random. Sometimes the value will be high, sometimes it will be low, and the probability of it being high or low is equal. So with random error, if you make the measurement over and over and over again and average the results, the random error should go away. And that's one of the reasons that we frequently make 4 measurements instead of just 1, because we can average them and reduce the amount of random error. So random error tends to cause imprecision. And then student B was precise but inaccurate, and inaccuracy comes from systematic error. This is a sort of error that tends towards being too high, or it tends towards being too low. And there are many different things that could cause this to happen. If you're measuring a liquid in a graduated cylinder and you're measuring the top of the meniscus instead of the bottom of the meniscus, all of your volumes are going to come out too high. They may be very precise, but they will be inaccurate because of user error. You're not using the instrument correctly. If the balance is not calibrated correctly, then your masses could come out all too high or all too low. So that's an example of systematic error. We'd like to reduce both of them. It's not always possible. Any questions?